Howdy everybody, Mr. Reed here. I'm going to go over for Precalc 12B, the limits introduction. Now some of you are here for pretty much the same sort of thing. It's not a bad idea to go back over it. A bunch of you are also missing, so this might be a little more helpful to you. So we'll go over what a limit is and some of the introductory things of how we're going to use it. And yeah, so we'll get started. So when it comes to limits, it's very important that we understand what a limit means. Okay, so the biggest thing is that limits are a little bit peculiar because a lot of times, from what we've seen so far, we care very much about what a function is at a certain value. For instance, if I write down f of 6, you know that what I mean is I'd like to evaluate f, whatever that function is, at an argument or a variable value of 6. And so I want to know what's happening right there. The peculiar thing with a limit is it is, instead of being interested about what's happening at a particular value, it says what's happening near or close to or approaching a value, which seems a lot the same, but it's significantly different, and because it's different, it will be very helpful to us, especially when we start looking at introducing some calculus concepts, whether that be towards the end of our limit section or when you first take an introductory calculus course. The idea is that approaching a value is explicitly different than being at the value, and we're going to see that in our first introduction here. So the idea that we're going to be looking at, first let's look at the notation. So for limit, it's LIM, notation-wise, x arrow a of some function or some statement is equal to just a value in this case. So the way that I would say this statement altogether is the limit as x approaches a of f of x is equal to L. And that's basically the way that we'll write a limit, is whatever variable you're interested in showing is approaching some particular value. You'll put that underneath of an LIM, and that is the notation for it. So probably the easiest way to understand what a limit is or what it does is to look at it graphically first. So again, the idea of a limit is we are going to take a look at what things do as they get really close to a value. So in class, I'd mentioned that we might want to say that what is a positive value, for instance, that is getting really close to 0. Positive values get really close to 0. Well, 1/1000th would be an example of that. The problem is, what if I want to describe the smallest positive value, or the positive value that's closest to 0? If you're asked that question instead, then it becomes a lot more difficult, because if you say, for instance, 1/1,000,000th, then I could go with 1/1,000,000,000th, and then you could come back with 1/1,000,000,000,000th, and we could go back and forth for a long time, and eventually we don't know how to say the words anymore that we're trying to represent, but we still have numbers that are smaller than every number that you could pick. So it's a little bit of a pickle when you're trying to say it gets really close to, so close that you can't really describe a smallest value between the number you're describing and the actual value. So one of the ways we do that is by using limits. And so it's kind of a loosey-goosey, hand-wavy sort of thing. If you want to get into a very numerically kind of like tight version of a limit, you would want to look at the epsilon delta definition of a limit and then derivative, because it is very, very particular in the way that it treats limits as not being hand wavy. Instead, you say things like, well, if you want to get within 1/1,000,000,000th, yes, we can find something that does that. If you want to find something that's even closer, we can do that too, just need a little bit better value to start with, or a tighter range. So what we're going to do instead is a little more hand wavy. So I'm just going to say gets really close to 0, and that will be peculiar, but it will work out okay, as long as you kind of open your mind to being okay with the idea of approaching and getting close to. So for this first one, I'm just going to scroll down here on my iPad, and the idea is that this value that we're interested in first is right here at 0. Piecewise functions are kind of the go-to when it comes to trying to describe how limits behave, because most of the functions that we've looked at so far are continuous over their domain, which means that you could draw every part of them where there is a value without lifting your pen or pencil. And because of that, they're kind of boring from a limit point of view. This particular function is a little more exciting. It has some kind of weird things going on here. And so the first place I wanted to look was at an x value of 0, which is at this little highlighted spot on here. So the idea is, if we come at this by coming in from the left-hand side of x is equal to 0, we see we're actually a part of a horizontal line where the value of that horizontal line appears to be 6. So coming in from this side, it looks like it should be a 6. If we are instead coming at the x is equal to 0 position, but we're doing that from the right-hand side, we'd notice that we're climbing up this sloped line. And as we do that, the closer we get to an x value of 0, the closer we get to a y value of 7. Now, because it appears like we should be a 6 from the left, and it appears like we should be a 7 from the right, the way we actually write that is that the limit as x approaches 0 of f of x is actually not equal to anything. It is instead DNE, does not exist. So that's does not exist. So most of the time we would just use DNE for that particular statement. Now, you might have a kind of a good question, which is, why, if the coming in from the right, you actually have a defined value there? So this spot right here, that's a colored in circle, which the only reason for that to be that way is because the function itself, f of 0, is actually 7. So why, if the function is actually 7, does the limit not exist? And that's because of what a limit is. So the limit is only describing what the values are approaching, not what they become. And that's a really important thing to remember as we're going to keep going here. So next up, if we instead take the x is equal to 3 value, which is down at this little, it's a corner, but at that pointed section of this graph, we would be able to notice that coming in from the left looks like we're going to be a 1. And coming in from the right looks like we're going to also be a 1. Since we are approaching the same y value, whether we're coming in from the left or the right, as we approach an x value of 3, which the way to say that is the limit as x approaches 3 of f of x, well, that actually is a value of 1. So that limit does exist, and it does give you a value of 1. The last one here is going to be the limit as x approaches 5. And so this one is another particular case that's important to look at, because this function actually does not have a domain value at x is equal to 5. So if we were to take a look at the domain, it would not include 5 at all. So not in domain. Because of that, it seems peculiar to investigate what's going on at that point, because it doesn't even exist for the function. However, the concept of a limit is only what looks like is going to happen as you approach as close as you possibly can. So as you approach as close as you possibly can from the left, it looks like we're going to be a value of 5. As you approach from the right-hand side, it looks like we're going to be a value of 5. That agrees, and so therefore the limit as x approaches 5 of f of x actually is a 5, even though the value itself does not exist for the function. So that's an important distinction, and kind of a good way to start looking at limits is to look at them graphically, be able to pull up a question like this one, make some comments as to whether there is a limit, whether it does not exist, and what that limit might be. All right, so next up, I'm going to look at limits by thinking about it in terms of a table of values. So in this particular example, came up with a really simple function. So f of x is equal to 3 minus x. Linear function, y-intercept of 3, negative slope, slope of -1. And so if I were to look at investigating this thing right here, so the limit as x approaches 2 of f of x, then what I want to do is not say what is the function at 2. I want to say what does the function become as we get very close to 2. So in a table, we have to do that with actual values. So just to kind of give you a trend, I've already entered in here 1.9, 1.99, 1.999, and then from the other side, 2.1, 2.01, 2.001, and those are, in both cases, getting progressively closer to the value of 2 from the left, and then getting progressively closer to the value of 2 from the right. So I've also evaluated the function at those numbers. So 3 subtract 1.9 is 1.1, etc., etc. So each of those hopefully should end up being the values listed there in the table. So if we take a look at all of those results, I guess you can say, so let's see here. If we just take this stuff over here and basically say, hey, what's the trend here? What is this becoming? Well, those values are all very close to 1. Now, not only are they close to 1, but the better we make our approaching part, so as we get closer to actually being at 2, the closer these values are getting to a value of 1. So this one and this one, it's pretty hard to deny that it definitely seems like there is a trend, and that trend is heading towards a value of 1. So from this table, we could probably feel pretty comfortable to say that the limit as x approaches 2 of f of x in this case, it does appear to be 1. All right, so the way that limits work, I guess you could say, can be explored by taking some smaller cases and seeing where they go from there. But in order to do that, we need to have some properties that make sense for what limits are. So if you specifically think of limits graphically, this is probably the easiest way to have this make sense, all the stuff that's going to come up next. So I'm going to have f of x as a function and g of x as a function, and in all the examples coming up, both f of x and g of x will have a limit. We're not even going to say what it is, but it will have a limit when x approaches a. And if you ever come across a c, then that's just a constant, and we'll just treat it that way. All right, so for the first one, the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So what this is saying is if you have a combined function by the addition operation, so we have a function in brackets there that is f of x plus g of x. So this combined function right here is basically just saying that if you have two things that are added and you would like to take the limit of it, if you split this apart into two graphs and look at the limit of each of them, the sum of those limits is the same as the limit of the graph that's the sum graph, or the overall added graph, which makes sense. So if you take some y values and you add them to some y values from a different function, then those y values, if the actual y values leading up to this place exist, they should add to give you just the additive total. So if this is approaching 2 and this is approaching 3, then the sum of that should be just the individual limits added together. So approaching 2, approaching 3, overall approaching 5. The same thing should happen down here for if we are instead talking about subtraction. So if you have two graphs and one of them is approaching 5 and the other one's approaching 5, and we take those two graphs and we subtract them, so all of the y values of one graph subtract all the y values of the other graph, then if they're both approaching 5, then together they should approach 0 when subtracted. Well, if we were to evaluate those limits separately and then subtract, we would also find that should give you a value 0. That makes sense. And so basically limits for addition and subtraction work the way that we hope them to. Next up, this is a constant multiple rule. So this is the limit as x approaches a of c times f of x is equal to c times the limit as x approaches a of f of x. So if I take a picture or graph and I double it, all of the y values are double what they used to be. So whatever they're approaching is double what it used to be. So if I have a function that is double what it used to be, then I could just take the limit of the function the way I know how, and then double it when I'm done, and I will get the appropriate answer for that limit. So again, that, if you think about it from a graphing point of view, should feel not too bad. And you could always play around in Desmos or something like that if you feel you'd like to take a look at that and see how it actually pans out. Next up, if we have the multiplication of two functions, again, in this particular case, if something's approaching 3, and then you're multiplying it by something that's approaching 2, then at that, well, let's just say not even approaching. If a value of one graph is 2 and a value of one graph is 3, then the value of the multiplication of those two graphs is going to be 6 there. So if one of the graphs is approaching 2 and one of the graphs is approaching 3, then the multiplication of those values that are getting tighter and tighter to 2 and tighter and tighter to 3, that has to also be getting tighter and tighter to 6. So we could take the limit of and find 2 and the limit and find 3 separately, and then we could multiply them together and we would get our overall limit. So again, the multiplication of two functions, if you want to know the limit of it, it's the same as if you could find the limit of them separately, and then we multiply afterwards. All right, so to go along with that, kind of like the addition subtraction that we saw first of all, this is the division limit property. So instead, if you want to take the limit of two functions that are dividing one another, then we can take those functions individually, divide them, and after we've taken those limits, and that ratio of the limits separately is equal to the limit of the overall division or ratio. The only exception to that is this goes all to crap if your bottom function or your bottom limit, either or, if that is approaching 0, then you are sunk. So if it is a 0, or you're getting values that are approaching 0, it just does not give you what it is. I guess the function itself could be a 0 and it still can work out fine. So maybe I misspoke there. It's more that the limit here, if this value approaches 0, then this division doesn't make any real number. So it will not be true that this will be equal to that. All right, in the last one, this is the limit of something that is experiencing an exponent, so it's raised to a certain power. That's equal to if you take the limit and then raise it to a power afterwards. And again, graphically, if you think about some function and we square the function, if the values of the original function are approaching 3, and then you square the values afterwards, those values should be approaching 9. The difference between how far off of 3 you are and then how far off of 9 you will be might be different because of the square function, but because we're going to be basically getting infinitely close to 3, then we will end up getting infinitely close to 9 as well. So whether we do that by taking the limit first and then raising to a power, or looking at the squared function and then evaluating the limit law basically say that those two things work the same way. All right, so we're going to look at these two very simple examples. So the first one is just the limit as x approaches a of just x. Now, if I said this to you out loud and I asked you to answer, I think you could answer it. So, as x approaches a, what does x approach? So if it sounds kind of nonsense, it's because it is. So the limit as x approaches a of x, so x is approaching a, so therefore the limit becomes a. And again, just from kind of the plain English way of explaining it, as x approaches a, x approaches a. But that's for the nice tidy function of just x. For the second one, we have the limit as x approaches a of c. Now remember, we had said at the beginning that c was a constant. So we can basically just say that since c is a constant, as x approaches a, c doesn't care. C is just going to stay c because it's a constant and it is not dependent on any change in x. So c it is. those two, I guess, values, if we know what goes on in those cases, we can condense every single limit that we're going to look at on the next pages to these two properties if we apply all of the other limit laws to go along with them. So for instance, if we take this particular one, which is the limit as x approaches 4 of x squared plus 5x minus 6. So I probably should have a bracket written around it on here. Oh, let me just add that in there. So something like this and this. That should be there. Now, if I want to evaluate that particular limit, and we want to do it the long, tedious way, because of course we do, we're going to use all the limit properties. Now, I'm going to over-apply them a little bit, because if I were to do this piece by piece, I could probably say something like this. So the limit as x approaches 4 of x squared plus 5x minus the limit as x approaches 4 of 6. So that is one of our properties. If we have a subtraction involved, you can take the stuff before the subtraction, take the limit of it, and subtract the limit of the stuff afterwards. We can also take this particular piece right here and do a sum. So I can take that one step further and say that this is the limit as x approaches 4 of x squared plus the limit as x approaches 4 of 5x minus the limit as x approaches 4 of 6. Tedious, right? So we're going to get there, and at this point I have one. The one at the very end, this one right here, it's ready to go, because that is actually the limit as x approaches something, so x approaches a, of c, because it's just a constant. That number is going to give me a 6 in the end, and we're kind of done with that. But I'm not going to evaluate it quite yet, but we could if we needed to. So the next thing is I'm just going to say the limit as x approaches 4. There's a rule that says if you have a power inside of a limit, we can evaluate the power after we have finished the limit. So we can take the limit as x approaches 4 of just x, then have it all squared. Plus, there's a constant multiple rule that says if you have 5 times something else inside that limit, we can take that out front as a constant and evaluate the limit of the other stuff and just multiply by that 5 after we're done. Lastly, this is the one we already said we know how to do. I'm going to just finish it off on the next line. So the limit as x approaches 4 of 6. First one, this one right here. The idea with that is we just said right here what happens in that case. The limit as x approaches a of x is a. The limit as x approaches 4 of x is 4. So we're going to get 4 squared, because we square after we're done, plus 5 times 4 for the exact same reason as the highlighted part on this last line, minus 6, because that's actually the other one up here. It is the limit as x approaches a of c is just equal to c. So as x approaches 4, 6 is 6. So there it is. We could evaluate that and get 16 plus 20. So that would be 36 minus 6 is 30. So we get a value of 30 in the end. Now, I am actually going to go on to a next one, but since this is getting a little longer than I thought, what I might do is I might leave this one for you to try out, and you can see if you get to something where you feel comfortable, like you've broken it down into things that just have either x in the end or just have a constant, and you're evaluating the limits of those. So if you'd like to take a try at that one, go ahead. And then what I wanted to discuss is this particular thing, which is kind of disconcerting because it kind of makes you feel like the limit thing is totally garbage. you may or may not have noticed that if we just plugged in the a value into the given function, you would end up with the same answer. So we got 30. We got 30 this way right here over, no, there. So that is opposite on my screen, so I'm going to get all messed up. Over there is how we actually evaluated the limit by using limit properties. What if I told you, just plug 4 into the function? So if we plug 4 into x squared plus 5x minus 6, again, probably if we're being a little bit more careful, we should put some brackets around those. Then you would just say, okay, well, x squared, so it's 4 squared is 16, plus 5 times 4 is 36, minus 6 is 30. Great, we get the answer. The limit existing and being equal to the function itself is actually what defines a continuous function. We're going to see that a little bit later on. But for the meantime, continuous functions are basically the most boring things to take limits of because of this property. If you know that a function is continuous to begin with, then you basically doing limits is plug the number in and go, because there's nothing that could go wrong as long as the function is continuous at that point. And you might just know some things about what functions are continuous at certain places and what ones are not. So that's why this one seems to be a little bit on the not so fun side. That should be good for now. I'll let you go and digest some of that. I hope you're staying safe, staying well, and remember to flatten that curve. Take care.